So last lecture, very exciting. We're going to briefly just look at something called collision theory and talk about how temperature affects energy in collisions, and then talk about something called the Arrhenius Equation. So first thing I want to talk about, and it's not on this slide, but what things need to happen for a reaction to happen? What happens? They have to collide. They have to not only collide, they have to collide with enough energy to get over that hump. What was that hump? Yeah, we have to have enough energy to basically qualify to be energetic enough to get over that hump and have the appropriate activation energy. In addition, they not only have to collide with the right energy, they have to collide at the right orientation, because there's little active sites where the collisions have to happen for the reaction to go. So those are two things that are really, really important, and that is collision theory, which you're going to need to know. And I'll revisit that in a second. But here in this picture is a graphical model explaining what happens when you heat up a reaction and how it affects the kinetics of the reaction. Graphical stuff is huge on the AP now, so you need to be able to look at graphs and interpret them. This particular one tends to confuse people for some reason. So what's happening here on this axis is energy. Okay? On the Y is number of molecules. So this is actually, my little ghetto drawing here is not very well done. These two things should have the same area underneath the curve, okay? Because the number of molecules aren't changing. We're just changing the energy of the molecules by changing the temperature. So this one is at 300 K. This one is at 400 K. This little dotted line here represents the activation energy. This is the energy that's required before the reaction molecules can actually react. In this picture, is the number the same? Yeah, it's the exact same activation energy. When you change temperature, activation energy doesn't change. What's actually changing when you change temperature in the reaction? Say you're going up in temperature. What's going on physically? Molecules are doing what? Colliding more because they have more energy. Think about, remember our average kinetic energy? Does anybody remember that equation? Yeah, 3/2 RT. All right, so as we increase the temperature, our average kinetic energy is going to increase. Since the average kinetic energy is increasing, more molecules are going to have the correct energy. So what this picture is showing, at a lower temperature, these molecules to the right of the activation energy are eligible to react. At a higher temperature, the only thing that happened was the entire curve shifted, allowing more molecules to have that required energy. Do y'all see that? All right, so it's literally just a shift of the curve. Did the activation energy change? No. Questions on this? So you need to be able to either look at it, interpret it, and interpret it, or to me, this is a great answer to the question, how does temperature affect rate of a reaction? Just drawing this out and doing a quick little explanation, saying that, hey, now more have the appropriate activation energy according to the above diagrams, this many molecules can react at this, at a higher temperature even more can react. Great explanation. Okay, so just be comfortable reading these and possibly redrawing them. So we can look at the effect of temperature on the kinetics. We can also now look at the effect of a catalyst on the kinetics of the reaction. So this would be my ghetto drawings, and then these are modern day drawings. We'll just look at the modern day pictures. They're much prettier. So yeah, this is how technology advances over the years. I just added this year. If you notice, do you see how both of the curves are identical in these pictures? Okay, so the number of molecules here all have the same energy in both pictures. But in this one, this is considered to be an uncatalyzed reaction. Catalyzed reaction, where this value here is the activation energy. So anything in the curve, underneath the curve to the right of that, is eligible for reacting. If I add a catalyst, you've said it a billion times, what happens to the activation energy? It what? What does the activation energy do if we add a catalyst? Lowers. So notice here, do you see how this is at a lower energy right there? Because this now is at a lower energy, do you see how you have more molecules available for reaction? So in this particular example, the curve didn't shift. In this one, the actual activation energy changed. Got it? All right. So again, be able to interpret this stuff, and this is catalyzed. Now we talk a lot about catalysts, and it's just catalyst, 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 and a lot of question I'm sure in your head is, well, how do catalysts really work? You're going to be responsible for knowing a little bit, just a smidge, about two different types of catalysts. One is called a heterogeneous catalyst, and one is called a homogeneous catalyst. And the word hetero or homo in this case refers to the phase that the catalyst is in compared to the reactants. The heterogeneous catalyst is usually solid, and it is a solid surface in which we pass gas over, and then the gas molecules are absorbed onto the surface, bringing them in closer proximity of each other, aligning them more appropriately, giving them the opportunity to react. Because if you think about gas molecules, how are they in space? They're going crazy, right? So yeah, they might be able to collide, but that orientation is going to be an issue. Here, they're kind of tamed, absorbed on the surface, reaction occurs, and then they're released. So what makes a heterogeneous heterogeneous is the fact that you've got a different state of matter in the catalyst than you do to the reactants themselves. The next slide is just another picture of that same kind of thing. Absorption and activation of the reactants, migration of the absorbed reactants on the surface, so they can kind of move around the surface in order to get to the right spot. Reaction occurs on the surface, and then release of the new products that have been formed. So that's an example of a heterogeneous catalyst. Good? A homogeneous or homogeneous catalyst actually exists in the same phase as the reactants. An example of this are enzymes. So you hear about lock and key, how in order for the reaction to happen, you need to have one of the reactants attached to the enzyme, which activates it, and then the other thing comes in, then you have the substrate and all this vocabulary. I don't need you to know any of that. I just want you to know that the catalyst is in the same phase, starts like this, ends up like this. Is it part of the mechanism? Sure, because technically if you were looking at like a diagram, we know the activated complex up here is the intermediate right when the collision happens. That could include the catalyst. Remember, what do we do with catalysts on our mechanisms when we add them up? What do we do with them? They cancel each other out, right? So this and this would cancel out in the mechanism, all right? So homogeneous catalysts, just know they are part of the same system. If we're in a gaseous reaction, the catalyst would be a gas. If we're in a liquid form or aqueous, so would the catalyst be. That's it. Not a big whoop-de-doo. Not that hard. All right. Now, what we want to talk a little bit more about is activation energy. Today, you're actually going to learn how to calculate activation energy using something called the Arrhenius Equation. All right. What is activation energy? Again, I'm just showing you the same picture you've seen a billion times. Activation energy is the energy required for reactants to make this intermediate. So in terms of how you calculate it, you go from reactants to the top of the peak. Delta H is the difference between the reactants and products. I'm hoping by now you're comfortable with this picture, okay? You guys have a flip in your slides, so this is actually one slide ahead, and we'll go back to the next one. So what this whole Arrhenius equation we're going to look at is based on, it's based on the collision theory. Again, in order to collide, we have to collide with enough energy, and it has to be at the appropriate orientation. So the Arrhenius equation is based on that. K is our friend. What? What is K? The rate what? The rate constant. The normal K we've been solving for now. 3 different ways. You know how to find rate laws. It's the K in the rate law. That K is equal to, and this is a division, by the way, in this exponent, some random A. And this A is what makes us enable. We're not going to ever use this version. We can't. It's too weird. This A enables us to describe the orientation. It's called the orientation factor. Every single reactant step of every mechanism in the whole wide world should have their own orientation factor, which is an issue. So we get to have a new version of this equation where this is not going to be a part of it. It's going to cancel out. E is the energy of the collisions. All right, and then this E over A is the activation energy. This is what we kind of want to always solve for, is our activation energy. R and T, what's capital R? It's not gas constant this time. Since we're solving for an activation energy, which R are we going to use? 8.31, the joules per mole K this time. Right? So always ask yourself, what am I solving for? If you're solving for something about gases like volume or pressure, then you use the gas R. But we're solving for an activation energy, so we use the energy R. You don't need to memorize the R, but both R's are on the paper, so you need to know which R to use. Watch your units. And so what do you think our temperature then needs to be in? Kelvin, because that's joules per mole Kelvin. Okay? This version of the equation sucks, like I said, because of this whole orientation factor, which causes a problem. Are we able to know the orientation of everything in the whole wide world? No. So what they've done, they've created this linearized equation where first they took the natural log of one reaction, then they took the natural log of another one, same reaction but different temperature and K, and then did a ratio of them, and the A's ended up canceling. So this is the new and improved version. However, I do not want you to memorize. You will be given that equation. All right? All you need to do is be a robot and plug and chug and solve. So what this is saying here, in order to figure out the activation energy, you need to know the K at a certain temperature, and then you need to know the K at a different temperature, because remember we talked about K's being temperature dependent? So given the combination of K and temperature of the same reaction, we can figure out the activation energy. Okay? Now let me show you something else. This is, I don't know if you think this is cool, but I do want you to know this. If I give you this equation, I might ask you, oh, you can't even see that. B is that canceled out A business. If I wanted you to graph K's and temperatures to find activation energy, you could. Looking at what I just did up there, what would I take the natural log of? I have a bunch of K's. I would take the natural log of K, and I would plot it against what? What's the X? 1 over temperature. If I do that, I'm going to get a line. How would you utilize this line to find activation energy? Slope is equal to EA over R. So what is activation energy equal to? No, what is activation energy equal to? Slope times R. That's how you would find activation energy graphically. So yesterday's lab technically had an extension to it. You saw how short and easy it was. It really wasn't meant to be that way. I just, with everything going on, I felt like we just needed to chillax a little bit on that lab. So yesterday, you guys found out that that reaction was what order? First order, right? So you knew you had to graph what and what to get first order. ln of concentration versus time. All right, so you guys did that, and you found a K. What temperature was that K at? What? Room temperature. So everyone had the K at room temp. The next part of the lab was supposed to be me assigning temperatures to all the other groups. And you were going to take your solutions, those syringes, put it in another water bath. And I would have said, okay, Peter, you do 30 degrees. Irene, do 40. Grant, do 0 degrees. And you were going to all run it again at a different temperature. So we'd have all these different temperatures, T1, T2, T3. You were then going to regraph as a first-order reaction because you knew it was first, and all find new Ks. Your Ks were going to be different. Then you were going to take those Ks and those temperatures, put them in your lists, and natural log of K on the y-axis, 1 over T on the x, and all find the activation energy. So that's kind of what the lab was supposed to be. If we didn't have a quiz, we could have done it, because everyone would have just done one more run at a different temperature, and then we would have shared data. But what I want you to know is if I show you this equation, you would know that you could figure out activation energy through graphing it. Okay? All right, any questions on that? So let's go ahead and just solve a couple problems on this, and then we'll be done. 2 more problems for the unit. It's exciting. All right. At 300 degrees Celsius, the rate constant for the reaction cyclopropane is 2.41 times 10 to the negative 1. So there's your rate constant at that temperature. At 400 degrees Celsius, the rate constant is this. So we have another couple. Calculate the activation energy for the reaction. So that should trigger in your head, oh, I need the Arrhenius equation. I will give it to you, but it's ln of K1 over K2, make sure I don't mess this up, is equal to EA over R times 1 over T2 minus 1. All right, so you're going to be a monkey, like I said, and just plug and chug. The only mistake students make here is mixing up the pairs. So I'm going to label this my first pair and this my second pair, so I can always put it in the right spot. So my K1 is 2.41 times 10 to the negative 10th divided by my K2, which is 1.16 times 10 to the negative 6th. If you switch these, it's fine. If you decided to make this one K1 and this one K2, it doesn't matter. Just make sure your T's align the right way. I don't know EA. I'm looking for that. What would be my R? 8.31 joules per mole K times 1 over T2. T2 is 673, because 400 plus 373, 273, sorry, 673, minus 1 over 573. And again, these have to be in Kelvin. All right, so I'm going to write down what first period got. Check it for me. They got E over A is equal to 2.72 times 10 to the negative 5th joules per every mole of reaction. The audience is checking. Anybody? You know what? That makes sense. You wouldn't have a partial joule. So, okay. So let's do, I think I just miscopied it. I do remember it being positive. Yeah, positive 5th. All right. So that's a lot of joules. And when you take organic chemistry, you're going to learn about cyclopropane being the most unstable cyclic molecule ever because its bond angles are so messed up, so strained that it's very, very, very unstable. So that thing decomposing is pretty high energy. All right? All right, the next one. This is it. This one will throw some things at you, and I just want to see if you guys can kind of figure it out. If the activation energy is blah, 1.0 times 10 to the second for this reaction, calculate the temperature change necessary to double the rate at room temperature. All right, so let me just go ahead and write this equation out again. All right, I am looking for a delta T, so I need both temperatures to do that. Some people wanted to make this whole thing just like a variable. You really can't do that. All right? We're going to have to solve for the temperatures individually. They do give me one hint here about one of the temperatures. What do they say? They say what? Room temperature. So that's about 25 degrees Celsius, which is 298 K. So we can make that one of our T's. So to find delta T, don't we need to solve for T2? Yeah? Okay. So what am I going to do? Because I only have activation energy. I know nothing about the Ks. Exactly. One of them is double. Why? When you double the rate, think about what a rate law says. Rate is equal to K times some concentration raised to an order. We're dealing with the same reaction, just at a different temperature. So our concentration for 1 and 2, these two things would be the same, and obviously the order would be the same. So if the rate doubles, what has to happen to K? It has to double. So we can just make stuff up. If T1 will be our starting K, what do you want to call it? 1. So what do you want to call T2 then? K2? 2, right? That's it. And so now we just plug it in. So we get ln of 1 over 2 is equal to solving, oh no, they give us E of A. So that's 100. 1.0 times 10 to this, does anyone see a problem? Kilojoules. Why can't I be in kilojoules? Not the rate constant. The R is in joules. So 100 times 1,000 is 100,000. Over, so this is joules, over 8.31 joules per mole. Okay. Times 1 over T2 is what we're solving for. T1 was room temperature. We're making a lot of assumptions here, and that's fine. They're just looking for a ballpark, like kind of what's going on. Say again? So our T2, did that answer the question? No, what was the question? Delta T. What's our final temperature? 303.2 minus our initial temperature of 298. So what is our delta T? 5.2 Kelvin. All right? Now, there's like a rule of thumb people use, and this proves that it's not exact. They usually say, oh, if you double, no, for every 10 degrees, the rate doubles. Well, sort of. I mean, that's 5 degrees. But this is just kind of yet a mathematical proof, again, that as temperature increases, rate increases. Yeah? Okay. Yep. We're comparing the same reaction 2 times. So we're doing the reaction, let's say, K times something. I'll do squared. We're doing this at 298. Then we're going to do it again at, say we'll do it at, what's double 298? 596. Well, I should, never mind. Whatever. We're doing it 2 different temperatures. This rate, these two, since it's the same exact reaction, it's going to be the same number. This is going to be the same molarity. Same molarity, same molarity. So if we're saying that the rate doubled from 1 to 2, the only thing that can happen then is K doubling. Okay? All right. That's it. Good job.